Hi students, this is Mr. Yao. Today we're going to talk about 7.2 where we will learn about chords, tangents, and inscribed angles. First, let's look at some more definitions. Tangent segment theorem. We have talked about tangent line theorem, and that's where when we have these tangent lines, they are perpendicular to the radius from the point of tangency. So here is slightly different. This one, tangent segment theorem, is saying if we have a point outside a circle, and this point is going to form these two tangent lines, and they are actually congruent. So now let's see how we can actually prove that. Given SR and ST are tangent segments, we're going to prove SR is congruent to ST. Something very important about these circle proofs is, even though we're working with circles, we're still going to use triangle proofs a lot of the time. So triangle congruence, which means whenever we have something, these lines in a circle, we're going to try to make some triangles, which is why the first step, we are going to connect PR, PT, and PS. And now you can see there are two triangles. And these two parts, SR and ST, we can clearly see that's actually part of the triangle, these two triangles. One is right here, PTS, the other is PRS. So these two triangles. And SR and ST seems like they are corresponding side. Now let's actually think more about how we can actually prove these two triangles being congruent. Because if we can, then SR and ST is going to be congruent with each other by CP/CTC. Let's look for some things that they shared in common. So clearly we see they share this side, PS, which means we already have a side. And we can't use ST and SR because we're trying to prove that. So we gotta look for other things. Now let's check the other pair of sides. We have this PR and PT. Well, if you look at it, they're both radii, which means they are actually going to be the same. So now we have two sides, we're gonna actually try to look for more things. And I mentioned at the beginning, this is tangent segment theorem. We also had tangent line theorem. So that means if we have a tangent line, these are going to be 90-degree angles. So now we have enough information. A shared line, we have another side that are corresponding that are the same, and we also have these 90 degrees. However, if you just look at the things we labeled, it looks like we're having side angle. It's not saying it's side angle side, because in that case, the angle needs to be in between the two sides. So not this one. But we also know side angle, that doesn't work. So we can't exactly use that. But upon further examination, we see, oh, we have this is a right triangle, we have this as a leg, and that shared side happens to be the hypotenuse. So now we know we're going to use HL to prove that these two triangles are congruent. That's the thinking process of this proof. Now let's actually go forward and write down the steps. PR and PT, they are the same because they are radius. And PS are congruent, that's reflexive property, that's the shared side. And then because SR and ST are tangent segments, by tangent line theorem, we know these two angles are actually 90 degrees. And with that, this is our H, that's our leg, and this is our H. We can actually use HL congruence to prove triangle PTS and triangle PRS are actually congruent. Last thing, we can actually conclude that SR and ST are congruent by CP/CTC. Now we have proved that theorem. Let's see how we can use it to solve some problems. First one, RS and RT, they're both tangents, so that basically means these two are the same. So we just set them equal to each other. 3x plus 4 equals 28. Minus 4 minus 4, 3x is 24, so x equals 8. Example 2. Still, they are both tangents, so we can set them equal to each other. 2x squared plus 5 equals 13, minus 5 on both sides. 2x squared equals 8, x squared equals 4. We're going to square root both sides, x equals plus minus 2. And you might be like, wait, but we can't have a negative length. Well, it's actually 2x plus 5. Even if you plug in negative 2, that's going to be 2 times the negative 2 being squared. That is still going to be a positive number, so that still works. Next, example 3. This example is more for you to think about where the tangent lines are and how they relate to the radius or not related. So you see the question already said these radii, the two radii we have, they are not the same. However, if you look at this circle on the left side, these two parts of the tangent segments, they are congruent. And then if you look at the one on the right, you will see in that right side, these two are still congruent. So which is why the whole thing is congruent. Which means even though we have different radii for circles, doesn't affect tangent lines that's sent from a common point. They can still all be congruent, all the tangent segments. Next, example 4. This one we're going to find the perimeter. And you can see that this side is given, this side is given. The only part we're missing is that little part. And from this common point, it's sending out two tangent lines. So that means even if this is 8.4, this side would also have to be 8.4 because they're from the same point. If that is 8.4, since the whole thing is 18.5, the leftover is going to be 10.1. And from this point, that is one part of the line tangent. This is the other tangent, so that part is also 10.1, which means the leftover from that side is going to be 12. So this little part we're missing is also 12. Now we just need to add them all together, 18.5, 22.1, and this side. So 18.5 plus 22.1 plus 8.4 plus 12, that is going to give you 61, which is the perimeter. Now we're going to try to find the missing angle. For this one, there are actually many different methods to do it, so I would suggest you try it out first, and then see if you actually have a better method, or if it's just a method. It doesn't quite matter if it's faster or slower, as long as you can actually look through the angles and get your final answer, you're good. So for this one, these are tangent lines, so I can have 90 degrees right here. And if this is 26, since these two are both radii, that means isosceles triangle, this would also have to be 26 degrees. Which means inside this triangle, this side would actually have to be 128 degrees. This whole thing is a quadrilateral, so I can actually use 360 minus the 190, minus the other 90, and then minus the 128, which gives me the question mark at 52 degrees. And of course, that's only one way. You can also find other ways to do it. Example 6, same thing. There are several different ways to do it. I'm going to do a way that I think works for me. Radius, radius. So this is an isosceles triangle, which makes that 61 degrees. And inside that triangle, if both the base angles are at 61, that means the center angle is going to be 58 degrees. Next, this is a tangent line, so this is 90 degrees. Now, if you look at this triangle right here, if that is 90 degrees and this is 58, that means the question mark would actually have to make up the rest, which is 32 degrees. And again, you have different ways to do it. And we play with the radius a lot to form isosceles triangles to help us identify the angles that we can use. Next, we have Chords Theorem. This one is saying if a diameter of a circle is perpendicular, so perpendicular is already set up, then this diameter bisects the chord. And of course, also the arc. So the key idea here is we already know it's perpendicular, then we can conclude it bisects. Now let's see how we can prove that. Like I said, many times when we prove circles, we are going to use triangles. So in that case, we're going to actually form some triangles. And when we form triangles, radius is a very helpful thing. So we're going to connect OD and OF. Let's talk about the logic first. We're trying to prove HD is congruent to HF. We can clearly see there's this shared side, and they're also both right triangles. And of course, these two parts, they're both radii. So since the right triangle, they share this side, we can again use HL to conclude about triangle congruency. So let's now go forward and see the steps. Next, OD and OF are the same, are congruent because definite radius. And then OH, that is our leg, our hypotenuse. And since we already know that that's perpendicular, which means it's 90 degrees, that's tangent line theorem. That's actually not tangent line theorem. This is a perpendicular definition. Perpendicular definition. And then we actually can conclude these two triangles are congruent by HL congruence. Last thing, CPCDC, we can conclude two corresponding parts, HD and HF, are congruent. That's the proof of Chords theorem. Now let's actually use the Chords theorem to solve some questions. Example 7. We're trying to find x. For all of these questions, I suggest you pause and try it by yourself first before you actually look for the answer. This is x, and since this part is perpendicular to a chord, that means the chord is being bisected, so this must be 10.6, which means we have a triangle right there. 10.6 squared plus 4.3 squared, that's going to give you x squared. And something I want to suggest is, even though it doesn't look like we actually have a diameter, that doesn't change anything, because we still have a little line segment that is going through, that actually is going through the center. So that means if I actually extend that portion, it is going to be a diameter, which means it's for sure going to be Chords theorem, that we can use the diameter, and we can use the, we know the diameter is perpendicular to the chord, so that means we can actually use the Chords theorem to conclude. So after solving, x is going to be 11.44. That's example 7. Example 8. This is a very similar thing, and in case it's not clear, x is this part, and 13.9 is that part. And we can see if we want to know x is on this little line segment, which means we actually want to know that part. And we see that part is actually a leg of a right triangle, and again, that little side, this is actually passing through the center, which means that's going to be part of the diameter. So I can use that to help me to solve. So since perpendicular, this side is also going to be 13.9, and here 35.2 is the whole diameter. That means the little radius is going to be 17.6. So we have this right triangle, and we can actually solve for this part. I'm going to just call that part question mark. Question mark squared plus 13.9 squared equals to 17.6 squared. If you finish solving, that part is going to give you 10.80. And in case you didn't notice, this part, the x and the question mark, they actually make up a whole radius. So that means if I want to find x, I'm going to use the radius 17.6 minus 10.8. That's going to give me x as 6.8. That's example 8. Next, we have inscribed angle. An angle whose vertex is on the circle. So inscribed angle is actually to the opposite of central angle. Central angle is when we actually use the center of the circle to form angles. Inscribed is slightly different from that. And when we have inscribed angle, the little arc being cut by the angle, that's called the intercepted arc. And of course, we're going to have a theorem, measure of an inscribed angle theorem. The measure of an inscribed angle, so this is 1/2 the measurement of the arc. The arc is right here. And if you remember when we learned what we learned in the last lesson, the measure of an arc is the same as the measure of its central angle. So basically, this is also saying it's 1/2 the measurement of angle AC. This is the central angle. If we actually want to prove it, you're going to need to connect and actually use some isosceles triangle to prove. So when we try to prove, there are 3 different cases because we don't quite know where the center is in comparison to our 2 chords. It could actually be one of the diameter. It could also be the center is inside the angle that we have, or it could be the center is actually outside the 2 chords that we have. Either way, for all of these, you're going to actually use the radii to make some isosceles triangle to prove. Now let's see how we can use it. Number 9. It's very important to be clear on which arc is facing which angle. So you see this question mark is actually this angle, and the arc that's facing is right here, the 90 degree. And since the question mark is an inscribed angle, and that is the arc it's facing, it's going to be 1/2 of the arc. So 90 degree divided by 2, which is 45 degrees. And that is the question mark for the first one. Next, the question mark is right here. You can see that portion of the arc is actually facing 45-degree angle. So since this is going backwards, the question mark this time is going to be 45 degrees times 2, which is 90 degrees. Next, y. We actually know the point y is what is asking about the question mark, so we're gonna play with the arcs first. So we see there's one thing that's given, this 118. That's facing this arc. Endpoint's right here and here, so it's facing this arc, which means by that inscribed angle, we can know the arc is actually going to be 236 degrees. And if you look carefully, this arc that we labeled also actually just have this left over that can actually make up 360 degrees. So if that's the case, 360 minus 236, that's going to give us 124 degrees. So this arc is actually 124. And now after we found out about that, you see the question mark is actually facing this arc. So the question mark would have to be 124 degrees divided by 2, which is 62 degrees. The last one in this example, the question mark we can see is facing this part of the arc. And if you didn't notice, all the other parts of the arc are actually given, so that means we can actually find the arc. So the arc is going to be 360 degrees minus 157 minus 121. We just need to get rid of the other two arcs to actually find out what this arc is going to be, and it's going to be 82 degrees. And since the question mark is actually facing this arc, that's going to be half of it. So 82 degrees divided by 2, that's 41 degrees. That's example 9. Next, example 10 is not exactly solvable, so we're going to skip it. Example 11. Measurement of t is kind of easy to find because the arc is right here, that's what it's facing. Measurement angle t is half of that, 48 degrees divided by 2, that's 24 degrees. Next, the measurement of QR. There are actually several different ways to find it, so I suggest you pause the video and try it out by yourself and see if you can figure it out. One way to do it is, well, I'll kind of mention different ways. You can either connect QR and actually play with the isosceles triangle right here to figure out about QR, arc QR, or you can actually connect here. You see the TR is a diameter, which means this part has to be 180, so if it's half of that, that makes this angle TQR 90 degrees. Because that's half of this arc, which is 180, so that's 90 degrees. And next, if that's 90, we can have a look at this triangle, then this part must be 40 degrees. If that's 40, and 40 is facing arc QR, QR must be 40 times 2, which is 80 degrees. That's example 11. And because of that, we can actually draw two conclusions. One, an inscribed angle is a right angle if and only if it intersects a semicircle. So you see it intersects a semicircle. The semicircle is 180 degrees. The inscribed angle is half of that. This must be 90 degrees. That's a guarantee for, it's not a theorem name, but it's conclusion that we can draw. Next, we have same arc theorem. If two inscribed angles of a circle intercepted the same arc, for this one is arc ABC, and because they're both half of that arc, which means they are actually going to be congruent. So if the angles are facing the same arc, the inscribed angles are going to be the same. Now let's use these to actually solve some questions. So the first one, we see this part is being represented, this other part is being represented. There doesn't seem to have any solid angles we can use. However, this arc, this angle right here is facing this side of the arc, which means it's going to be twice of this angle. So it's going to be 32x. Something else you can always use in a circle is the full sum of angles inside the circle. So in this case, you can see all three parts of the circumference are being represented. And that makes up 360 degrees. 16x plus 5 plus 32x plus 22x plus 5, that equals to 360. After solving, x equals 5. That's example 12. Example 13 is actually kind of similar. We have this 9x plus 1, and it's facing this side of the arc. And you see the other two parts of the arc are given, so we're going to use 360 degrees minus 80 degrees, which is 280, minus 78 degrees, that's going to be 202 degrees. And that's what it's actually facing. If that is 202, we can say the measurement angle FGC is half of this arc. So it's going to be 202 divided by 2, 101 degrees. And that happens to be the angle we are using x to represent. So 9x plus 11 equals 1. X would have to be 10. That's example 13. Next, example 14. This time we're going to find the question mark. So you see the 34 is being labeled. So that means this arc must be 68 degrees. And if that is 68 degrees, you can clearly see this SQ is the diameter. That means this whole thing would have to be 180 degrees. The question mark is 180 degrees minus 68. It's going to be 112 degrees. And that shouldn't be too bad. Here's another way you can do it. You can see this angle right here is facing a diameter, so semicircle, that makes this 90 degrees. And if this part is 34, that means the other part must be 56 degrees. And if that's 56, the question mark of the arc is facing that inscribed angle, so double that. 56 times 2 is also going to be 112. Last one example, 15. Question mark is right here, and you can see again, it's facing, it's including a diameter, which means if we actually connect them, this would have to be 90 degrees. And if that is 74, the inscribed angle right here, that would have to be 37 degrees. If you didn't notice, that 74 degree is actually facing this angle as well, which you can also use in another method. We're going to focus on our triangle. If that's 37, the question mark would actually have to be making up the other part of the triangle. So 180 minus 90, 90 minus 37, that is going to be 53 degrees. That is example 15. That's everything for 7.2. Thank you.